icon, a window will open. Go to the new case. First, we have to insert 3 buses. Go to the draw network, click on the bus. Just write the name bus number 1. This is the size for better visibility. Go to the bus information. We know that the voltage of the bus is and it is select bus. Just click on the system select bus. Similarly, for bus 2, just change the name bus 2. Voltage is considered as 1.0 because we don't know the exact voltage at this bus, so we have to calculate the bus voltage. Similarly, for bus 3, just change the name bus 3. Again, voltage is considered as 1.0. Now we have to put the voltages, so go to the field and click on bus field. Just write here 1.05 because this is the select bus voltage and click on OK. Similarly, for bus 2 and bus 3, now a generator is connected at bus number 1. Again we have to give set point voltage. We know that bus voltage is 1.05, so just change it into 1.05 volt. It asks about power. We don't know the exact amount of the power, just put randomly any value. This is the size for better visibility. You can see here the values are in whole values. In order to get the values in decimal, just double click on it and put here from 0 to 2 for real power. Similarly, for reactive power, again replace 0 with 2. Now we need transmission lines connected from bus number 1 to bus number 2. Just double click on it. We know that the impedance of the bus number 1 to 2 is this. Just insert these values. And again go to display, increase it to 2 for the better visibility. This is pie chart, just double click on it. Write here 1000 and click here. Click on total power MVA. Change the color if you want. I choose blue color for the normal power flow, and these are the colors browns and yellow for the overloading capacity. Similarly, put the transmission line from the bus number 1 to bus number 3. We know that the impedance from bus number 1 to 3 is this one. Just put the values in the table. Similarly, put the transmission line from the bus number 3 to bus number 2. Now we have to insert the load bus number 2. We know that the load on bus number 2 is this. Put these values.
Click OK. We know that again these values are in whole values, convert into decimals, replace 0 with 2. Similarly for reactive power, again put the load on bus number 3. We know that bus number 3 has the load. Put these values. Again we have the values in the integer form. In order to convert into the decimal, just replace 0 with 2. Similarly for reactive power, replace 0 with 2. It seems that system is fully connected. Now we can run the simulation in order to check whether it is running correctly or not. For this purpose, just go to the tools and click on the play button. You can see system is working correctly. Voltage at bus number 2 was 0.98. We have the answer from the book. The answer is 0.98183. It gives the 2 decimals because we selected the 2. If we want to replace the more decimal, just replace with 5. You can see the answer is exactly same. Similarly for bus number 3, just replace the 2 decimal with 5. You will see the answer. You can compare the answer with the original answer. Select bus real and reactive powers are also shown. You can compare with the answer available in the book. Both answers are correct. For better visibility, just go to the online display options, animated flows, and change the size from 10 to 50. You can see it looks more attractive. Now we have to calculate the line flows and line losses. So for this purpose, again go to the draw field and transmission line field. We'll click here. This shows the power flow from the bus 1 to 2. Similarly, for bus, click here for reactive power flow. Put the transmission line here and click on the megawatt losses. This will show real power losses for the bus number 1 to 2. Again for reactive power losses. So this shows the reactive power losses from bus number 1 to 2. Again put the transmission line field at the end of the transmission line 2 to receive the megawatt flow at the bus number 2. It shows the reactive power flow from the bus number 1 to 2. You can compare the answer with the answer given in the book. Both are exactly same. Only negative sign is given. This negative sign is due to the connection of the buses. Again for the bus number 1 to 3, we calculate the real power flow and reactive power flow. This shows the reactive power flow from the bus number 1 to 3. For the losses, just click on here. It will show you the megawatt losses. Similarly for reactive power losses, click again for the real power flow reached at the bus number 3. Similarly, reactive power flow reached at the bus number 3. Again, power flow for bus number 3 to 2. Click again for the real power flow reached at the bus number. Just click on transmission line field again here and click here on megawatt flow to calculate the reactive power flow from the bus number 3 to 2. Click on megawatt losses to know the real power losses from the bus number 3 to 2. Again click on the bus to calculate the reactive power losses from the bus 3 to 2. Finally, click on the end of the bus number 2 to know the power flow reached at bus number 2. Now repeat the same process for the reactive power flow reached at bus number 2 from 3 buses. Now we can run the simulation. It looks more attractive with all the voltages, real powers, losses shown in the system. To make it more beautiful, we can write some text. Right here, Gauss-Seidel load flow method. You can put a rectangle for more attraction. Change the color if you want. I change the color from green. You can change by your choice. Put in text here. We want to calculate the total real power losses of the whole system. For this purpose, just go to field, area field, click here. It will give you the total real power losses of the system. Similarly, again put the text for the total reactive power losses of the whole system. Again, go to field, click on area field, right here. It will give you the total reactive power losses. You can see this total megawatt losses is the sum of the losses 8.5, 5 and 0.8 is equal to 14.3. Again 33 is equal to 17 plus 15 plus 1.6 is equal to 33.6. To make it more attractive, you can put here a rectangle box. Change the color if you want. So by this way, we can design the Gauss-Seidel load flow method in PowerWord simulator, and we can simulate any example from any book. Last thing, if we want to know how to determine the admittance matrix, just go to the case information and then solution details. At the end, click on Y bus. It will show you the admittance matrix. You can see the admittance matrix is almost equal to the admittance matrix shown in the book. You can compare all these values with the values of the system. I hope you enjoyed this tutorial. Thank you very much. If you like this tutorial, then don't forget to like it and subscribe my channel.